To build a steel aircraft for the sake of reaching a speed of 3,000 kilometers per hour, only to burn 3/4 of its fuel during the climb. The Bristol 188 is the most expensive and perhaps the most unsuccessful research project in the history of British aviation. How did the machine, assembled using unique argon welding, equipped with temperamental engines and a complex wing shape, turn into a nightmare for production engineers? Why did the project designed to fly at Mach 2.5 fail to reach even Mach 2, while its longest ascent into the sky turned into a struggle for survival due to an empty tank? And how did the designers manage to spend millions on a flying laboratory that turned out to be useless? Watch the video to the end. Today we will analyze the secrets of the Bristol 188 design and find out why this supersonic aircraft was never able to accomplish its tasks. Let's begin. The 1950s were a time when aviation was changing faster than ever before. Jet engines had only recently ceased to be a rarity. Aircraft were breaking the sound barrier one after another, and every nation with its own aviation industry wanted to be the first to reach places where no one had really been before. Britain participated in this race on equal terms with the strongest players. But British engineers faced a problem more acute than many others. They were developing a reconnaissance aircraft that was supposed to fly at a speed of about Mach 3, and for this, they simply lacked data. This future reconnaissance aircraft was named the Avro 730. The machine existed only on the drawing boards, but even then it was clear that at such a speed, the aircraft would encounter a problem that designers of the previous generation had never even thought of. The skin begins to heat up, not just a little, but critically. Metal that holds its shape perfectly at normal temperatures can behave in a completely unpredictable manner at Mach 3. In Great Britain, no one knew exactly what happens to an aircraft that maintains such a speed for hours. There was not a single machine capable of testing this in practice. So the military department made a decision: if such an aircraft does not exist, it must be built separately, solely for this purpose. Thus, a specification was born, unlike the usual requirements for combat aircraft. The new aircraft was not meant to intercept anyone or spy on anyone. Its sole task was to fly fast for a long time and not disintegrate from within while doing so. Calculations provided specific numbers: a speed above Mach 2.5, which is about 2,900 kilometers per hour, a flight altitude of 20 to 25,000 meters. For comparison, modern passenger aircraft fly about 2.5 times lower. Several British aircraft manufacturing companies submitted their proposals. One of them planned to simply take an existing fighter and modify it to meet the new requirements. This was the fastest and cheapest path. But the contract went to the Bristol company, and its engineers chose a much riskier path: to build an aircraft from scratch, specifically for this single task. It was meant to be not a combat machine, but a flying laboratory, an instrument with which the British aviation industry intended to peer into realms where no one had ventured for so long before. The contract was signed. But everything that depended on it from then on was contained within a few sheets of the technical specification, and it was precisely in those sheets that the main problem of the future aircraft was hidden. The technical specification for the future aircraft occupied only a few pages, written in dry language without a single extra word. But behind this dryness lay a requirement that no one in British aviation had yet attempted to fulfill. It was not just about speed. Many aircraft of that time already briefly crossed the sound barrier, accelerating for a few seconds and then slowing down again. The new aircraft was intended for something entirely different. It had to maintain a speed above Mach 2.5 not for an instant, but for a prolonged period. The reason was simple. The engineers needed to understand what happens to the aircraft's skin not at the moment of acceleration, but after prolonged heating. Metal behaves differently when heated for a second, and completely differently when heated continuously for tens of minutes. For this, a special material was required. Ordinary aluminum, from which most aircraft were made, simply lost its strength at such temperatures. The choice fell on a special grade of hardened stainless steel, capable of withstanding heating up to 500 degrees Celsius. But that was not all. A separate point in the specification required that the engine design allow the power plants to be removed and replaced without redesigning the entire aircraft. The aviation industry in those years was developing several types of supersonic engines simultaneously, and the future aircraft was meant to serve as a platform for testing them. 3 prototypes, that was the final requirement. 1 for ground static testing and 2 for flight. Several companies joined the struggle for this contract. One of them, English Electric, proposed the most economical option, to take an existing combat aircraft and adapt it to the new conditions, a shorter and cheaper path. And here it is worth returning to a single line in the specification that almost no one paid attention to at the time. The requirement to maintain high speed for a long duration, rather than briefly, meant that the aircraft would need significantly more fuel than a conventional fighter of the same weight. No one at that moment had calculated exactly how much. The contract was awarded to the Bristol company. Its engineers rejected simple solutions and set about designing the machine from scratch, fully tailored to the conditions of this requirement. The task was accepted. It remained to decide what literally to build the aircraft from, in order for it to spend so much time in the scorching air at speeds that almost no one had sustained for so long before. Every single weld on this aircraft was made by hand. One mistake by a welder, and the entire section was scrapped. But before talking about welding, we must understand why the engineers abandoned conventional aluminum in the first place. With prolonged heating above 300 degrees, aluminum begins to lose its strength literally before one's eyes, and the aircraft was destined to spend hours under precisely these conditions. The Americans, facing the same problem on their own supersonic reconnaissance aircraft, chose titanium, a light and strong material, but temperamental to process, and in those years, still rare and expensive. British engineers took a different path. They chose stainless steel, a material much heavier but well studied and understood by the industry. Moreover, they selected not just one grade of steel, but 2 at once. For some components, they used steel with a high chromium and nickel content, stabilized with titanium. For others, they chose a special chromium steel, the same kind used in jet engine turbines where temperatures are even higher. The outer skin turned out to be particularly unusual. Inside it was a honeycomb structure, similar to a bee's honeycomb, but made of metal. Such a design retains its shape under heating significantly better than a solid sheet. And the designers fundamentally decided not to apply paint to this skin. It simply would not have survived the operating conditions. Then began the real problem. Heavy chromium steel turned out to be extremely difficult to rivet in the conventional manner. Rivets created weak points precisely where the skin was expected to withstand the most intense heating. Engineers had to develop a new welding technology almost from scratch. An electric arc burned inside a protective cloud of inert gas, argon, which prevents the metal from oxidizing at the moment of melting. The weld turned out almost monolithic, without bubbles or cracks. It sounds elegant on paper. In practice, however, the workers had to learn to weld sheets of metal less than a millimeter thick without burning through them and without leaving a single defect. This turned out to be an incredibly slow and temperamental process. Every large fuselage panel passed through the welder's hands in parts, weld by weld. One wrong move and the panel went to waste instead of the aircraft. Construction deadlines stretched month after month precisely because of this bottleneck. The aircraft was supposed to take to the air as early as 1957. But while the workers were only mastering the welding of the new material, a separate list of complaints was already accumulating against the aircraft's design itself. From a distance, this aircraft resembled a sharpened pencil. Long, narrow, with almost not a single protruding detail. It was because of this silhouette that the factory workers nicknamed the machine the Flaming Pencil, a nickname that later found its way into official documents and press articles alike. The fuselage was indeed stretched to the absolute limit in length. Its diameter was determined by just one component, the pilot's ejection seat. The cockpit protruded only barely above the skin, so as not to create unnecessary air resistance at high speeds. The cross-section of the fuselage itself was made oval rather than circular like most aircraft. This shape allowed the pilot to be seated in a normal sitting position, and the main landing gear wheels to be retracted vertically, right inside the fuselage. At the same time, almost the entire internal volume of the fuselage was occupied not by instruments or systems, but by fuel tanks. The wing turned out to be perhaps even more unusual than the fuselage. It was straight, but with a thickness of only 4% of the chord length, meaning extremely thin. And the leading edge of this wing did not run in a straight line from root to tip. The sweep angle changed 3 times across the span, an almost straight angle closer to the fuselage, about 38 degrees behind the engine nacelles, and 64 degrees at the very tip of the wing. Wind tunnel testing showed that precisely such a broken leading edge provided the required airflow behavior in two regimes simultaneously, both near the speed of sound and significantly above it. But finding the solution was not immediate. Already constructed wing models had to be completely redesigned after the very first wind tunnel runs revealed serious flow issues. The wing turned out so thin and the leading edge so sharp that ground crews servicing the aircraft on the ground were issued special gloves. Ordinary skin would simply be cut by such an edge. In each wing, right between the fuselage and the wingtip, one engine was positioned. The size of the nacelle was only slightly smaller than the diameter of the fuselage itself. This arrangement solved several problems simultaneously and created new ones at the same time. Each nacelle had to open easily for power plant replacement, as the aircraft was conceived as a testbed for several types of engines at once. The canopy and windshield were made of quartz glass. Ordinary organic glass would simply have begun to melt at such speeds. In case of cockpit overheating, a cooling system was provided. Looking ahead, we must say that this system never had to be used for its intended purpose. The shape was ready. It remained to breathe life into it, and for this, something was required that was capable of pushing this needle through the air faster than sound. The engines that this aircraft ultimately received were not originally designed for it at all. They were handed over to the machine almost by chance after two other programs were canceled at once. Initially, the designers planned to install Rolls-Royce Avon engines, the very same ones meant for the large Avro 730 supersonic bomber. The logic was simple. Two projects were being developed in parallel, meaning the power plant could be standardized. But in 1957, the bomber program was canceled. Along with it, the engines intended for it vanished. Their production was simply halted. The designers of the future research aircraft had to urgently look for a replacement. The choice fell on another engine, the Gyron Junior, developed by the de Havilland Company. And here, coincidence worked in favor of the program. This engine was originally created for another aircraft, the Saunders-Roe SR.177 Interceptor fighter. When that program was also canceled, several completed engines along with their afterburners were left idle. They were transferred to the new project. Each of the two engines developed a thrust of about 4,535 kilograms in dry thrust. With the afterburner engaged, at sea level, this figure rose to 6,350 kilograms. And at altitude, due to ram air pressure, the thrust became even higher. The engine had one truly advanced feature for its time. Its afterburner was smoothly adjustable from the minimum setting to full power without sudden jumps. Until that moment, no British aircraft had flown with an engine capable of such smooth afterburner regulation. The air intakes received movable cones inside, which changed position depending on the flight speed, allowing air to pass freely at subsonic speeds and adjusting the flow to the engine's needs at supersonic speeds. Separate anti-surge bypass doors vented excess air to avoid compressor stalls. And the nozzle assembly in the tail section changed its shape, regulating the exit speed of the hot gases. On paper, it was a powerful and technically advanced power plant. The engineers were pleased with the choice. It had enough thrust to accelerate the aircraft to the required speed. But engine power and its appetite for fuel turned out to be two completely different stories. According to the original plan, the aircraft was supposed to take to the air as early as 1957. But 57 passed, then 58, then 59, and the machine still did not fly. First, not a flying machine, but a specially constructed airframe intended solely for ground testing was sent for trials. In May 1960, it was delivered to a research center for structural testing. The airframe was loaded in both cold and heated states, simulating the very conditions for which the entire project had been initiated. Only a year later, in April 1961, the first truly airworthy prototype was rolled out of the factory gates. On the same day, a trial taxi run was conducted on the runway. It seemed that only weeks, not months, remained until the first flight. But the flight did not happen. The entire summer and autumn were taken up by engine trials right on the ground. The aircraft was started, the turbines spooled up, instrument readings monitored, then the engine shut down, analyzed to see what went wrong, and started all over again. Problems were discovered precisely where the engineers least expected them, in the air intakes and the afterburners. the movable cones inside the air intakes did not operate as smoothly as calculated on paper. The afterburner either failed to reach the required mode or, conversely, suffered uncontrolled fuel surges. Every month of delay cost money, but no one yet knew that the most expensive problem had not even manifested itself yet. While the engineers were dealing with the air intakes, time was not standing still for the rest of British aviation either. Another British fighter, originally designed for Mach 2, had gone through testing during these same years, was accepted into service, and was already serving in operational units. Meanwhile, the aircraft that was supposed to exceed its speed by almost 1.5 times still stood on the ground with a disassembled engine. Parallel to the ground testing, another inconspicuous but extremely important effort was underway. Dozens of scaled-down models of the aircraft were tested in wind tunnels. Some of the models were even mounted on modified rocket boosters and launched into free flight from a range on the coast of Wales to understand the behavior of the design at real supersonic speeds, albeit without a pilot on board. By the beginning of 1962, the problems with the air intake and the afterburner were finally resolved. 8 years after the project received the green light, the aircraft was finally ready to take to the sky. The aircraft lifted off the runway, and at that moment, no one yet knew that it would never actually reach the coveted supersonic speed. The morning of April 14, 1962 did not differ from dozens of previous mornings at the Bristol company's airfield, except that this time, everything was actually supposed to work out. 8 years had passed since the military department first formulated the requirements for this aircraft. 5 years had passed since the date when, according to the original plan, the machine should already have been flying. Hundreds of labor hours had gone into welding the airframe, dozens of models were tested in wind tunnels, and months were occupied solely by ground testing of the engines. And so, after all of this, the first flight turned out to be surprisingly modest. An experienced test pilot took the machine into the air from the factory airfield and headed towards a military test center located in another part of the country. No sharp maneuvers, no supersonic speed, only a smooth, calm flight at subsonic speed. 23 minutes. That was exactly how long the first flight of the aircraft lasted, for which 8 years and a colossal sum of money had been spent. The machine landed safely at the new airfield, without a single complaint regarding the operation of its systems. In this lay the main characteristic of that day. The first flight turned out to be so smooth and predictable that there would be almost nothing to say about it, were it not for the contrast with the years of difficulties that had preceded it. From the airfield where the aircraft landed, it performed another 16 flights, also at subsonic speeds, and also without incident. Engineers gradually expanded the boundaries of the tested regimes: speed at various altitudes, landing gear operation, and the behavior of data logging systems. Then the aircraft was returned to the factory, where it made its final 2 flights in its testing program. In September of the same year, the machine was shown to the general public for the first time at a major air show, where the aircraft was demonstrated in flight for 4 consecutive days in front of thousands of spectators. The public met the unusual silhouette with genuine delight. Few of the spectators knew that the aircraft shown to them had not once exceeded the speed of sound. The first machine proved the main thing. The design was capable of flying and doing so reliably. But this machine could not test what all this was started for. For a real supersonic trial, a second machine was needed, the one destined to bear the main brunt of the program. The first machine proved that the design was capable of flying, but the real task of the program had to be solved by the second machine. On April 26, 1963, this second machine took to the air for the first time. It was accompanied by a chase plane. The pilot of this aircraft monitored the behavior of the new machine from the outside, ready to notice any malfunction before the instruments could register it. Behind the controls sat the same test pilot as a year ago. The first flight lasted about 30 minutes and again took place at subsonic speed. But unlike its predecessor, this machine was created precisely to cross the sound barrier and sustain it. The test program was structured gradually, step by step. First came the verification of the most basic aspects: stability at different speeds, landing gear operation, and the behavior of data logging systems. Only after ensuring that all of these systems operated reliably did the engineers begin to slowly expand the speed envelope. The first attempts to cross the sound barrier looked modest. A short dive, a fraction of a second at supersonic speed, a velocity slightly above Mach 1, and then a return to a calmer regime. Every such jump was recorded by the instruments, and every second of the aircraft's behavior at that speed was later analyzed by engineers on the ground. In the summer of that same year, progress quickened. Over 2 months, the aircraft performed about a dozen flights dedicated specifically to the supersonic regime. By the end of July, for the first time, they succeeded in maintaining a speed above Mach 1.83, not in a dive, but in level flight. That is, in the very regime for which all of this work was undertaken. On paper, everything looked correct. But the sky, as usual, was preparing its own adjustments. The culmination came in mid-November. In the 47th flight of the program, the aircraft reached a speed of Mach 1.88 at an altitude of about 11 kilometers. This corresponds to approximately 2,243 kilometers per hour. This figure remained the highest speed that this program would ever achieve. The engineers on the ground received this news with mixed feelings. On one hand, it was a record for British aviation of that era. On the other hand, the originally stated goal was still very far away. And the most unpleasant part lay not in the speed itself, but in how much time the aircraft was actually capable of sustaining it. The longest flight of this aircraft lasted 48 minutes, and 34 of those minutes were spent merely climbing to the required altitude, 70% of the fuel. This is neither a typo nor an exaggeration. Precisely that much kerosene was burned before the aircraft could even begin the task for which it was built. It can be imagined like this. Fill your car with a full tank of fuel for a long trip out of town, only to find that 3/4 of the gasoline evaporated before you even drove off your street. This was roughly the reality of this program every time the aircraft took to the air. The reason lay in the engines themselves. Yes, they developed enough thrust to accelerate the aircraft to the required speed, but to climb to an altitude of 11 to 20 kilometers, from where supersonic runs could finally begin, the turbines had to operate at their limits for long minutes. And operating at the limit meant maximum fuel consumption. By the time the aircraft finally reached the required altitude and speed, the tank was already nearly empty. Only a few minutes remained, sometimes less than 10, before it was necessary to turn around for landing, simply to avoid running out of fuel in the air. Yet the entire point of the program was precisely the duration, not the mere fact of achieving speed. The engineers needed to understand what happens to the aircraft's skin after long minutes of heating, rather than during the first seconds after acceleration. Metal behaves differently if heated continuously for an hour, and completely differently if heated for 3 minutes. It was precisely this difference that they failed to measure. The problem was not limited to fuel consumption alone. Individual flights were cut short due to fuel leaks directly in the tanks. The design, engineered for extreme thermal loads, turned out to be not perfectly leak-proof. Moreover, the aircraft required a speed of about 480 kilometers per hour just to take off, and this also created additional difficulties during every start. Engineers tried various solutions, changing the flight profile, reducing climb time, and adjusting the engine operation mode. But this did not resolve the fundamental issue. The aircraft simply could not physically carry more fuel than the volume of its tanks allowed. And these tanks had been designed based on completely different assumptions about fuel consumption back at the design stage, many years before the first flight. A speed of Mach 1.88 became the limit for this program. But to understand why it was precisely here, and not higher, one must peer inside what was happening to the aircraft at the moment of transitioning through the sound barrier. The test pilot who flew the machine more often than anyone else later described this transition in one word: smooth. The aircraft calmly passed the very moment when the speed matched the speed of sound. No jerks, no shaking, no unpleasant surprises. But a bit further, beyond this mark, an entirely different behavior began. Both engines did not operate in perfect synchronization. At high supersonic regimes, a phenomenon occurred in them that engineers call compressor stall, a sharp disruption of the steady airflow inside the compressor, because of which the engine's thrust drops for a fraction of a second and then sharply returns. If this had occurred in just one engine, the aircraft would have simply shuddered noticeably. But this happened most often non-synchronously in both turbines at once. One engine would momentarily lose thrust while the second continued to operate at full power. The thrust asymmetry between the left and right sides of the aircraft forced the machine to simultaneously yaw and pitch, completely unpredictably, precisely at the moment when the pilot least wanted to fight the controls. It was this instability, rather than the speed itself, that turned out to be the main limitation of the program. Climbing higher meant ascending into a zone where compressor stalls occurred even more frequently and sharply. It is worth comparing the figures. The original specification demanded a speed significantly above Mach 2.5, steadily maintained for a long period. The achieved result was Mach 1.88, and even then only for a few seconds of level flight. The difference between what was promised and what was achieved was not in the details. It was almost a third of the stated goal, and that is not to mention that even the takeoff of this machine required a speed of about 480 kilometers per hour, unusually high for aircraft of that time, which in itself created additional risk during every takeoff. By the end of 1963, it became final and clear. The issue was not with a single component that could be refined in a few months. The problem was systemic, affecting the engines, the fuel system, and the very logic of the entire program at once. The project was not canceled due to a single mistake. It was canceled because fixing this mistake would have cost more than building the aircraft anew. By the end of 1963, engineers understood perfectly well what the problem was. The engines were simply not suited for this task, neither in terms of fuel consumption nor in the stability of operation at extreme regimes. The logical solution seemed to be replacing the power plant with something more advanced. But replacing the engine on this aircraft did not mean simply unscrewing one turbine and installing another. The nacelles, the air intakes, and the entire wing structure around the engine were designed for the specific dimensions and operating modes of this exact pair of turbines. Installing a different engine would mean practically redesigning a significant part of the aircraft from scratch. And the aircraft was already 5 years behind its own schedule, and had noticeably exceeded its original budget. While engineers were calculating the cost of such a redesign, the surrounding situation was changing in a way that did not favor the program. By the time this machine was only just beginning its first supersonic flights, another British fighter, designed for Mach 2, had already been in service with the Royal Air Force for several years. The urgent need for a separate experimental aircraft to study this speed was becoming increasingly less obvious. Across the ocean, meanwhile, work was underway on their own reconnaissance aircraft, built of titanium and capable of steadily maintaining a speed of about Mach 3, the very goal that British designers had originally set for themselves. That machine was already in the final stages of development and was scheduled to enter service in just a couple of years. In early 1964, it was officially announced that all work on this aircraft was to be discontinued. On January 12th of that year, the machine made its 51st and final flight. By the time of its cancellation, the total cost of the program had reached £20 million sterling. For those times, this made it the most expensive research aircraft in the history of British aviation. £20 million, 8 years of development, dozens of constructed and wind tunnel tested models, hundreds of man-hours of manual welding, and in the end, a result that never came close to the originally stated goal. From an accounting standpoint, this looked like a failure by any measure. But if one looks at this story a little more broadly, it turns out that not everything invested in this program vanished without a trace along with the project's cancellation. Not everything invested in this program disappeared without a trace along with its closure. Let us start with the material around which the whole idea of this aircraft was built. For the first time on such a scale, British engineers gained practical rather than theoretical experience in working with stainless steel in a real flying airframe. They learned how it reacts to hours of heating, how each weld behaves after dozens of heating and cooling cycles, and precisely where the weak points arise. And here begins the real paradox of this story. The collected data turned out to be insufficient for the designers of the future supersonic airliner to confidently choose the same material. In the end, they went a different way and built their aircraft from a conventional aluminum alloy rather than steel. This is precisely why the top speed of that airliner subsequently amounted to Mach 2.2, noticeably less than what had originally been planned for the machine we are talking about today. An interesting thing emerges. The main contribution of this program to aviation history was not a successful material, but rather a clearly defined boundary. Thanks to this experience, the designers of the future supersonic airliner knew in advance what was best avoided. But besides the airframe material, the program left behind a vast body of much more practical data. How oils and hydraulic fluid behave under prolonged heating, how bearings and landing gear tire rubber react, how the quartz glazing of the cockpit remains transparent at high temperatures. Every single one of these seemingly minor details later came in directly useful during the testing of the future airliner. The system for transmitting data from the aircraft to the ground deserves special mention. For its time, it was incredibly advanced. Instrument readings were transmitted in real time to a ground station, instead of simply being recorded on film for decoding after landing. This technology was decades ahead of its time, and later became the standard for flight testing. Let us not forget the engine either. The experience gained while working with this power plant, the first British gas turbine engine, originally designed specifically for sustained supersonic operation, subsequently aided in the development of another engine. This engine was later installed both on the supersonic airliner and on another promising British combat aircraft of that era. And there is one more detail, almost ironic. The stainless steel welds that gave the engineers so many headaches during manufacturing turned out to be so strong that the surviving specimen of this aircraft stood for decades without a single crack in its structure. For a program that formally failed its main task, this was an unexpectedly small but real victory. The aircraft, which had been deemed a failure, quietly turned out to be one of the stepping stones in the foundation of the most famous supersonic airliner in history. Two machines, built to the same drawing, went through the exact same testing program, but their fates diverged completely after the closure of the project. For several years, both machines stood idle at the factory airfield. Neither of them ever took to the air again. In April 1966, it was decided to transfer both of them to a military shooting range. There, they were turned into targets for shooting practice, just as was done in those years with dozens of other decommissioned aircraft. The first machine, the very one that had made the very first flight in 1962, ended its history on that shooting range. Almost nothing remained of it. The second machine was more fortunate. In 1972, before it could be completely dismantled for targets, the aircraft was removed from the range. The machine was disassembled, the engines removed, and it was transferred to the Royal Air Force Museum as an educational exhibit. It is there, in the museum located in Shropshire, that this machine remains to this day, the last surviving specimen of the program we have been talking about for this past hour. There was also a third machine, that very airframe which from the beginning was intended solely for ground testing and was never meant to fly. Its fate turned out to be even less noticeable. After the completion of structural tests, the airframe was sent for scrap, and absolutely nothing was preserved of it. There is also an almost amusing detail in this story. The first flight prototype once managed to appear not only in engineering reports, but also in cinema. It flickered in a British feature film filmed in 1962 near the factory in Bristol. For a few seconds, this unusual machine found itself in the camera lens not as a secret development, but as part of the cityscape. 20 million pounds, 8 years of development, 51 flights by the second machine. A speed that never caught up to the originally declared goal by almost a third. Formally, this was the most expensive research program in Great Britain of its time, and by all reasonable standards, it could be called a failure. But consider the material it tested for durability. The data on the behavior of oils, rubber, and glazing under extreme heating, the telemetry transmission system that was decades ahead of its time, and the experience with the engine, without which the power plant of the future supersonic airliner would not have appeared. Perhaps that is why this program cannot be called truly useless. It did not reach the goal it set for itself, but it paved the way to a goal that no one had even thought of at the moment the contract was signed.